my fault because there was a misprint in the expression for the operators A and B. Okay, I guess this is the source of this confusion. So for A, we had a diagonal operator. Yes, A was 1, minus 1, I guess, 0, 0, and this is a number, real number. And again, and B, it was written 1 here, 0, 0, and then minus 1, 1, 0, sorry, 0, 1, 0, right? This is what was written. Now, with this choice, one may be a little bit confused because if A is real, this is Hermitian, clearly. Okay. But this is not Hermitian, right? For any choice of B. No? You agree? Because this block here, when you take the Hermitian conjugate, so what is B dagger? Is B star, the complex conjugate. This is 1, 0, 0, and this is 0, 0. This is minus 1, 1, 0, right? Okay. So this block here flips a sign, no? Is minus that, right? So B dagger is different from B, right? So this is not an Hermitian operator. In fact, what I meant was plus here. If this is plus, then for B real, this is Hermitian, right? However, it doesn't mean that you cannot diagonalize simultaneously A and B. Okay? Remember that we said that for Hermitian operators, any Hermitian operator can be always diagonalized, which is true, but it doesn't mean that if the operator is not Hermitian, it cannot be diagonalized, right? Is a sufficient condition, but it's not a necessary condition, right? So, okay, there is nothing to say about this. This is Hermitian, but this operator here, with the minus here, with the wrong sign, it is not Hermitian, so it would not be an observable for any physical system because an observable must be Hermitian, okay? But it can still be diagonalized, right? Because, I mean, forget about this one. This block here, instead of having real eigenvalues, okay, if this was Hermitian, it would have real eigenvalues. So take this matrix here, 0, minus 1, 0, this block here, okay? This is not, this is anti-Hermitian, right? It takes a minus sign, right? When you take the Hermitian conjugate, because it is antisymmetric. This means that it has not real eigenvalues, but purely imaginary eigenvalues. What are the eigenvalues for this matrix?
Plus I and minus I.
Yeah, plus or minus I, right? So, okay, but okay, it can still be diagonalized. Doesn't matter, right? You see, to get an Hermitian matrix here, either you put a plus here, in which case the eigenvalues of this matrix would be plus 1 and minus 1. Right? Or you put an I, or you choose a matrix which is B is 1 here, like that, 0, 0, 0, 0, 0, I, say, minus I, 0. Okay. This is Hermitian now, because the minus sign that you get here is compensated by the complex conjugation, right? And the eigenvalues of this matrix here are not plus or minus I, but plus or minus 1, real, right? In fact, you know that this 2 by 2 matrix here is one of the Pauli matrices, right? Is what we usually call sigma 1. So let me introduce that. This is sigma 1, Hermitian, traceless. Sigma 2 is essentially this matrix here. Actually, let me put a minus here. This is sigma 2, 0, minus I, 0. So both square to 1, the square of sigma 1 is 1, the square of sigma 2 is 1, they both have eigenvalue plus or minus 1. And then there is sigma 3, which is diagonal, is 1, minus 1, 0, right? You know that, right? These are the Pauli, sigma Pauli matrices. Okay. So to get an Hermitian operator, either you put this or this, sigma 1 or sigma 2 here, and that will be Hermitian. But as I said, even if you take this choice, which is what is written on the notes, this is not Hermitian. This is Hermitian, okay? And by the way, there is no choice of B that makes this Hermitian, right? Because there is 1 here, so B can be real or imaginary, it doesn't matter. This will not be Hermitian operator. Okay? But the diagonalization can still be done. Because diagonalizing this or this is the same, right? The only thing which changes is the eigenvalues. But the diagonalization, so the conclusion is that, so these have a common eigenvector, which is the obvious one, which is say 1 is 1, 0, 0, right? This is eigenvector of both this and that, right? The problem is with this part here. This part, this is just proportional to the identity here, right? And this is instead off diagonal, right? But you can still diagonalize this. And the unitary matrix is the same that diagonalizes this one, right? I think some has done this exercise, forgetting about the hermiticity or whatever, right? Because you can check that if you take just this block here, eigenstates of these are, I think it's 1i, then we call it this plus, and minus is 1 minus I. Right? So this is the original, the simple thing due to this part. And this is the eigenstates, these are the eigenstates of this part here, or this part here. Okay? Check. Let's check it. Apply 0, 1, minus 1, 0 to this, for example. This is just a normalization, doesn't matter, right? What you get? You get I minus 1, right? But this is what? This is nothing but I times 1i. So this is the eigenvalue. So this is an eigenstate of this with eigenvalue I. For the other case, 0, 1, minus 1, 0. You have 1 minus I here. This is what? This is minus I, right? Minus 1, right? This is what? Minus I, 1 minus I. And this is the other eigenvalue. So the only difference is that the eigenvalues are purely imaginary instead of being real. But this and that are eigenstates both of this and that. So then once you diagonalize this block, this doesn't do anything to this for the reasons that we said the other day, because this is proportional to the identity. So the matrix, the U is essentially, U is what? 1, 0, 0, the first. The second is 0, 1 over root 2, and the other is I over root 2. And then you have 0, I over root 2, so 1 over root 2, minus I over root 2. This is the matrix which diagonalizes this one and this one at the same time. Okay? If instead you had what was the original choice, the correct choice that I had in mind, you put here 1, 1. This is a symmetric matrix. This is Hermitian when B is real. Right? What are the eigenstates of this matrix here? Of 0, 1, 1, 0. Well, are very simply related to this. One is 1 over square root 2, 1, 1, and the other is 1 over square root 2, 1 minus 1. These are eigenstates of this matrix with eigenvalue plus 1 and this eigenvalue minus 1. That you can derive by the standard procedure of computing the eigenvalues and the eigenvectors, like we did for the. So then the U, which diagonalizes both of these, is this. Is 0, 0, 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root 2. Okay. Instead of i's here, you have plus 1, minus 1. This is the thing that diagonalizes this. Okay? So, as I said, the fact that an operator is Hermitian is what we want for various reasons, because it has real eigenvalues, can be always diagonalized, but this is not a necessary condition. Let me mention to you what is a more general condition. If you have two operators, if you have one operator, A, suppose A dagger is different from A, so it's not Hermitian. Okay. Then A can be diagonalized if A dagger is equal to 0. That is, if A commutes with its Hermitian conjugate. Okay? The Hermitian conjugate is not the same, but it commutes with the original operator. If this happens, then you can be sure that this operator here, though it's not Hermitian, it can be diagonalized. Why is that? Because you see, if you have A and A dagger, it's a very simple argument. You can always take the sum and the difference of the two. This is Hermitian, right? Let me call it X. Because the Hermitian conjugate is the same, right? It's the same as X dagger, right? So this is Hermitian. But there is another combination which is Hermitian. What is it?
This is A minus A dagger over I.
All right. If I take A minus A dagger times I over I, let me call this Y, this is also Hermitian because this flips sign when you take the Hermitian conjugate, because A dagger becomes A dagger minus A, right? Minus, but this changes signs. The I changes sign, so this is Hermitian. So you have a pair of Hermitian operators, x and y, that can be diagonalized individually because they are both Hermitian. But they can be diagonalized simultaneously. Why? Because x commutes with y, right? If this is true. Right? So if you can simultaneously diagonalize this and that, then you are done. Why? Remember, our purpose was to diagonalize A. So you have u x, u dagger x, u is dx, and u dagger y, u is dy. These are diagonal matrices. Because this is true. Once you have this, how you can get A? Well, it's clear from here, right? To get A, you have to take a combination of x and y, which gives A. What is it?
X. Okay.
X plus I y is equal to A, right? No?
And vector. Oh, it's a vector.
Sorry?
Divided by 2.
Yeah, divided by 2. Right. This is 2A. So at the end, you can get A, the diagonal, these are diagonal, you take this combination, you get A. Right? Okay. So this is the general thing. The operators for which this is true, they are called normal. An operator is normal if it commutes with its adjoint. So if this happens, then you can diagonalize it, okay, even though it is not Hermitian. Okay. This is was just a remark, just in case. So the conclusion is that this exercise, although it had this misprint here, you could still carry over the procedure, okay, of simultaneously diagonalize the two. You have any questions? Because some of you said that they wanted to discuss this. I don't know if this was the question.
I have a question, Prof. Can a Hermitian operator share the same eigenstate with the non-Hermitian operator?
Well, this is an example here, right? Yeah, eigenstates, yes. The example here, we found a basis. Let me rewrite them, which is 1 root 2, 0, 1 over root 2, and then we have, what was it? I erased it. Yeah, 0, then I, 2 over 2, and then I don't remember the signs, but you have them, minus, minus, okay? These three are eigenstates of both this and this.
Okay.
Yeah, so the answer is yes. Yeah. Sorry, this was another, no, this was a different problem, right? this is this. No, let me write. This is 1, 0, 0, right? This is the common to that. And the other is 0, and this is, in any case, the answer is yes, but let me write the correct thing. 1 over root 2, I over root 2, 0, 1 over root 2, minus I over root 2. Okay? Yeah, this was the correct. This is eigenstate of both. This is eigenstate of both, and also this.
And by using this matrix, we can diagonalize again A.
Sorry?
It's already, matrix A is already diagonalized.
Yeah, the A is a diagonal, but the problem is this. To diagonalize this. Yeah, you're right. This is already diagonal.
Then if we use this unitary matrix and sandwich A between the dagger and its own, the eigenvalues of A won't be changed?
No.
Okay.
Because this does not do, this is the same argument that we said, right? This, what it affects only this block, right?
Yeah.
But this is the proportion to the identity, right?
Yeah.
Is minus 1 times the identity, then we put it like that. So whatever you do here, this part here, to take U dagger U, this won't affect this part. Because this is the identity. Right? If I call this matrix. So the structure is 1, 0, 0, and then U. But U is this. Right? So if I do this, the following operation to A, I apply to A this thing. This is 1, minus 1, minus 1, and 0 everywhere else. And here I apply this U here, which is 1, 0, 0, 0, 0, and then the block. And then I apply the Hermitian conjugate on the left. This is, yeah, this goes to that, 1 over root 2. This is I over root 2. And then here is minus I over root 2, 1 over root 2, right? The Hermitian conjugate of this thing. If I do this operation, this is U minus 1 or U dagger, this is U, and this is A, right? Okay? This is the same as A. Doesn't change anything.
Yes, understand, sir. Thank you.
So this is the argument, the general argument that I discussed the other time, applied to this particular case. The point is that this block here is just proportional to the identity, is minus the identity. And so, whatever you do this, when you conjugate, it doesn't change A. A remains the same. So the only thing that U does is to change B, to make it diagonal. So this is this can be checked by explicit calculation. All right. So let's proceed now with this mini review of rules of quantum mechanics, the principle, the rules of the game, so to speak. So we introduced states and operators, right? And observables. Observables, I remind you, are Hermitian operators, essentially. In the finite dimensional case, they are Hermitian operator, and the property is that the eigenstates of these operators, of the observables, can always be used as basis, orthonormal basis for the vector space. Okay, in the finite dimensional case, this is automatic. There is never any exception. And okay, we discussed also what happens in the case where one is dealing with infinite dimensional spaces, where operators in general are differential operators, as you know. Okay, and so the spectrum of this operator has an infinite number of eigenstates and eigenvectors, and not only that, but there can be also a continuous spectrum, not just a discrete spectrum. And so this is the most general situation that one can face. But let me continue with what one could summarizing. What are the principles in which quantum mechanics is based? Okay. So the first one is we already said it. Okay, a state of a system is a vector, say V, or let me put it psi, of some vector space. This is understood at some time, right? Not say, right? We fix some time, and this is what is there. So this is the first thing. The second thing, you have we associate physical quantities to observables, that is Hermitian operators. And then the third thing is that the possible outcomes of measurements of of A being physical quantities are the eigenvalues of A. So identify physical quantity with the corresponding operator, okay? So this has some set of eigenvalues, right? A, say lambda I is lambda I, lambda I. Lambda i's are real. And so the statement is that if I measure the physical quantity corresponding to this operator A, what I get is one of the eigenvalues of the operator A, right? And then now is the probabilistic interpretation. So to introduce that, what you do, you have your state, psi, and you expand it in eigenstates of the observable A. Okay? So you expand it, Ci, lambda I, okay, where Ci's are complex numbers. This can always be done. Of course, these are orthonormal, right? Lambda I, lambda J is delta Ij, and suppose we are considering discrete spectrum to simplify things, and no degeneracy for the moment, also to simplify things. Then you can expand your state in this basis, right? And so the crucial thing is that the probability getting lambda I in a measurement of A is given by, say, let me call it Pi, is just Ci mod squared. Okay, C is a complex number, the modulus squared is a non-negative real number. Okay, which is also, as we observed, lambda I psi mod squared, right? Because Ci is just you take lambda here, lambda j, say, and this project on Cj. Okay. So this is greater or equal than 0. Can be 0 if this is 0, there is no component. Depends on the state, of course. Okay. The state psi may not have any component corresponding to lambda I. Okay. And of course, this being a probability, there is a crucial requirement is that the sum of the probabilities, 1 to say some b, must sum to 1, right? Because if you make any, when you make a measurement, for sure you will get some eigenvalue, right? So then there must be probability, the sum over all the probabilities must add to 1. Okay? And so this is the condition which defines a probability. Okay? So this is the main feature of quantum mechanics, right? This probabilistic interpretation. Probability, what do we mean by probability? What does it mean, probability? It means that, in principle, you should think of making the same measurement many times. Okay? A big number of times. Okay? So you have your system in the state psi, you make a measurement of A. Then take another copy of the system in the same state and you make another measurement and so on. Okay? When the number of this measurement becomes very large, then you define the probability by the frequency in which the eigenvalues appear, right, in your sequence of measurement. This is the way you define the probability, right? Probability 1 would mean that every time you make the measurement, you get the same eigenvalue, right? This when this happens. It can happen, right? If psi is precisely one of the eigenstates of A, right? If psi is one eigenstate of A, then all the Ci's are 0 but 1, which is equal to 1. Right? In which case, well, 1, again, you see, up to a phase, right? If I multiply this by a phase e to the I alpha, I don't change anything. So if psi is, say, lambda j up to a phase, then pj is equal to 1 and all the other p's are equal to 0. Okay. So this is the probabilistic interpretation of quantum mechanics. So there is, this is the main feature. No? So even knowing the state precisely, right? You know that the system is in some state psi does not fix the values of the observables, but there is such a probabilistic interpretation, right? So this is, I think, should be well known. So once we have this probability interpretation, then there is a notion of average value of the observable, right? How would you define the average value? it is denoted in this way, which means, well, let me define it in more practical terms. Well, so you have done your huge number of measurements, you have your eigenvalues, you associate to them probability obtained from this big number of measurements, right? And then clearly you can define the average value A would be what? Would be the sum, the weighted sum of the eigenvalues, right? Weighted with what? With the probabilities, with the respective probabilities, right? This is what you would call the average value, right? The eigenvalues appearing with probability close to 1 count more than those which appear probability very small, close to 0, right? This is the natural. So this is the average. In the state. It depends on the state. Right? And it can be written as what is called expectation value. It's also sometimes called expectation value. And can be expressed as a matrix element of A in the state psi. That is, this A, defined in this way, is also equal to this number here. Matrix elements of the observable A in the state psi. Okay? Why is that? Well, let's plug in the, so what is this? This is sum over I and J. This is the bra is Cj star, right? Lambda J. So this is this, right? This is A. This is Cj. I can take out Ci, sorry, here, right? The cat Ci, lambda I, right? This is what it is in general, right? But these are eigenstates of A. So this is lambda I times the state lambda I, right? And then these are orthonormal. This gives a delta ij. And so this gives sum over I, Ci modulo square lambda I, right? But Ci modulo square is Pi, so we recover this expression. Okay? So these are the physical quantities that you can, that has physical meaning, right? Because the probabilities have physical meaning in the sense that I explained, and also the average values are related to the probabilities and eigenvalues, so they have physical meaning. Notice that also here, if I multiply this psi with the phase drops from this calculation, right? The overall phase. Okay? So if you plot, if you do this experiment, that is, you have your physical quantities, you make these measurements, okay? And you plot the probabilities corresponding to the various eigenvalues, right? You will have some distributions, right? So these are the lambdas, this is p's. You have some distribution, right? Which depends on the state. Clearly, in classical mechanics, if you say I am in that state, that is, I take a point in phase space, then all physical quantities have a unique value, right? You plug in the expression for the, say, the energy, the phase space point, and you get a number. There is no probabilistic notion, right? And so in quantum mechanics, we say, okay, there is this distribution of probabilities. Clearly, if you have a situation where the state is such that the distribution phase is of this form, right? Very much peaked around some eigenvalue, lambda bar, say. So the sharpest is this distribution, the closer you are to to the classical case, right? Because in the classical case, we know there is one value, that's all. There is no spread, right? No distribution. But quantum mechanically, there is this spread of probabilities. But if this spread is very small, then you can say that you are close to a classical situation, right? So there is a way to measure how far you are from a classical case, right? Like you do in statistics, no? And what is this measure? Well, this is the notion of variance of an observable in a given state. Okay, the notion of variance, which somehow measures how far you are from a classical situation, right? So this is denoted by delta A. Okay, so we have the expectation value of A, which is some number here. So take A minus that expectation value. Then clearly the expectation value of this thing is 0, right? Because A minus A is 0, right? Because this is a number, right? The expectation value of this number is A itself. And then this is A minus A, right? So this is 0. So there is nothing here. Okay. However, there is something if you consider the square of this thing. If you take A minus A expectation value, all square, and you take the expectation value of this thing here. This is some operator, right? The square of A, and then this is a number. This is the identity, no? Here. Understood, there is identity. What is this? Well, this is A square. I develop this square, right? Minus 2 times this times that expectation value. This is minus 2A squared. Right? And then plus A squared. Notice here, not to be confused, there are 2 things here. This is the expectation value of the square of the operator A. And this is the square of the expectation value of A. Okay? So these 2 and 1, this becomes A squared minus A squared, right? This is what this is. And this is, although it doesn't look like, always greater or equal than 0, right? Because of this, because this is equal to that. This is the square of an operator. This operator is Hermitian. So the square of an operator, the expectation value of it is always greater or equal than 0. Okay. So there is such an inequality, which if you write it this way, is not obvious, right? Because it's the difference of 2 things. So classically, this would be 0, right? Because classically, everything is equal to that. This is the same as that. Right? So delta A is defined to be the square root of this. Because this is a non-negative real number, so you can take the square root. And this is what is called the variance. So this is what is the meaning of this? This is how much the distribution is spread over around the expectation value, right? Think of a Gaussian distribution. Gaussian distribution, you have something like, right? X, this is P of X probability. So clearly the expectation value, the average value of X is this here, right? Is the P, right? And what is the delta X? The variance is just the size of this curve, right? This is delta X, right? The smaller is delta X, the more P you have here, right? If this is very flat, it means that your eigenvalues are sort of distributed randomly. I mean, they are very far from what you would have as a classical situation. Remember, we are in a given state. It's always understood that this is the same as psi A psi, right? And A square is also, right? A square is psi A square psi, right? So we are in a given state. So this is the meaning of this variance. It gives an idea of how much quantum, so to speak, you are far from a classical situation. Clear? Is it clear? Yeah, if you have a Gaussian distribution, right, think of this e to the minus x square, x minus x naught squared, right, over 2b squared or something like that, right? This is x naught. Clearly, and then 1 over n, such that the integral of this thing must be 1, right? This is what you expect from a probability distribution. So there is some n, there is some normalization. This is a Gaussian integral, right? Dx, this is equal to 1, so this fixes this thing here. Should be d over 2 pi or something like that. You should do it. Okay. And clearly, if I, so this is, say, P of x. P of x is without the integral, right? P of x is n, say, is the probability distribution. And clearly x, the expectation value of x is integral of p dx times x dx. And if you do the calculation, you would get this is x naught, right? And clearly, expectation value of x minus x naught is equal to 0, like that. And but you can compute x minus x naught square integral e to the minus x naught square to d square 1 over n. And this is what gives the variance, essentially. And the variance clearly is related to this d, is essentially d, right? The bigger is d, the more spread is the distribution. So this is what you have in this. If you have this Gaussian distribution, this is what it is. So you can do the same definition apply to this thing. Right. Now, let me just mention one thing which is very important, which is related to the variance of, now, variance of two, suppose you have the two observables, A and B. So you have observable A and B, they are represented by emission operators, okay? So you have delta A, delta B, for each of them, right? You are in a state psi, of course, given state psi. Now it can be, there are two possibilities, either for the commutator A and B, which is nothing but minus BA. Okay. Can be 0 or not 0, right? What happens if it is not 0? So that is, the two operators don't commute. So they cannot be diagonalized simultaneously. Okay. So then one can prove very simply, actually, the famous Heisenberg relation, uncertainty relation. There is a lower bound for the product delta A times delta B. But remember, these are two numbers. The variances are numbers. Have dimensionful. They are dimensionful because they are, for example, the energy, the angular momentum, the position. But they are not operators. Okay. And so the relation is that this is greater or equal than 1/2, I think, the expectation value of the commutator AB. But this in general can be need not be positive, so the modulus of that. Okay. Yeah, this is the. So you can prove this, one can prove this relation, which is Heisenberg. Particular case of this is the famous Heisenberg commutation relation, right? The uncertainty relation where for X and P, position and momentum, which have a canonical commutator, and so this is the right hand side we will see in a short time would be H bar over 2. So there is this surprising relation between the variances of two non-commuting. If A and B commute, okay, this says just this is greater or equal than 0, so there is nothing there. There is an empty statement, right? But if A and B is not 0, this is bounded by this relation. Okay. Now, to prove this, you use, this is a consequence of Cauchy-Schwarz inequality. Is a it's sketched in the notes how to prove it, but it's not. So Cauchy-Schwarz inequality is the statement that alpha, right, times beta, if you have two states like that, this is greater or equal than alpha, beta, most square, right? This is the norm square of alpha. This is the norm square of beta. Right? This is the same as alpha norm square. This is the same as beta norm square, right? And this is bounded by the scalar product of alpha and beta, modulo square of that. This is Cauchy-Schwarz inequality, right? Now, this comes from applying this inequality to a particular, you have to choose some convenient alpha and beta, okay? And the convenient alpha and beta is very simple, is, alpha is A minus A on, remember we are always in a state, given state psi, okay? That is fixed. And beta minus the expectation value B. These are two particular vectors obtained by applying this combination A minus expectation value A, B minus expectation value B on our state, the system is the state psi. Okay. And so this is what enters in this thing here. Okay. And so alpha, this thing here would be what? Alpha beta would be psi A minus A. Remember, A is Hermitian, so there is nothing here. This is the same as that, right? Because this is Hermitian, and this is B minus B and psi, right? This is beta, and this is alpha, right? No? So, okay. Now the trick is that, you see, here we have a product of two operators, right? This is an operator, this is another operator. If you have the product of two, let me call x and y, two operator x and y, x is this and y is that, you can always write it as the sum of the commutator of x and y plus the anti-commutator of x and y, half of it, right? This is the same as 1/2 xy plus 1/2 xy. But this is the anti-commutator. This is xy minus yx. This is xy plus yx, the plus. This is the minus, this is the plus. Right? Because this is the opposite order cancels between these two, right? Okay. And then the step is the following. So this is the product of two Hermitian operators. This is the commutator, this is the anti-commutator. Now, what about the properties of the commutator and the anti-commutator? If these are Hermitian, what is the commutator of two Hermitian operators? What do you think?
Shiro?
Anti-Hermitian.
Because they don't commute in general. Is anti-Hermitian, right? If you have xy minus yx, you take the Hermitian conjugate, no? This flips the order, right? You remember that, you know, right? Taking the Hermitian conjugate of two operators exchanges the order, right? This is yx minus x1, right? Dagger, but these are Hermitian, so this is the remove. And this is minus x1, right? Because it's the other, no? This is minus the commutator. So this is anti-Hermitian. And the commutator, since there is no minus sign, if just flip the order, you have the two orderings, but they give the same, right? Because both come with the plus. And so this is Hermitian. Okay? Now, the expectation value of an Hermitian operator is real, right? So we have that alpha beta is equal to expectation value psi of what? Of the commutator, right? Of the commutator plus of the anti-commutator, right? Say, let me write it, yeah. A minus A B, right? Plus anti-commutator A minus A. Oh, this is okay, right? No, this gives back the original thing. Now, so this is anti-Hermitian, and this is Hermitian. Now, the expectation, so this is the expectation value of an anti-Hermitian operator plus the expectation value of an Hermitian operator. Now, the expectation value of an anti-Hermitian operator is purely imaginary, right? Of anti-Hermitian is imaginary. Expectation value instead of Hermitian operator is real. Right? This you can prove easily, right? Hermitian operator picks a minus sign, anti-Hermitian operator when you take the star, and so it is purely imaginary. The other is purely real. So this thing here is something so alpha beta is something real plus I, actually this is imaginary, so imaginary plus real, right, number, no? So this is a complex number, real part is this, imaginary part is that, no? Now take the modulus square of this. So let me write in this way. R real part plus I capital I. Okay? This is the structure. No? Real part plus I imaginary part. If I take the modulus square, alpha, beta, modulus square of this, what is this? Is the modulus square of this complex number. So this is R square plus I square. No? Modulus of a complex number. Real part square, imaginary part. But this is greater or equal than E squared, right? These are positive. Right? But what is E squared? This is involves the commutator precisely. This is what? This is 1/4 because there was a 1/2, but you take the modulus square becomes 1/4. Modulus square of the expectation value of A and B. Because remember, we have the commutator of this with that, but what matters is only the operator part, right? The other numbers of the commute. Okay? So remember from where we started? We started from here. Right? We have that this is greater or equal than this part here, right? This is what we call it. So this means that that is also greater or equal than that, right? But this thing and this thing are just, this is delta A squared, and this is delta B squared. So if you take the square root of both sides, you get delta A times delta B is greater or equal than 1/2 the modulus of the expectation value of the commutator. Okay. So, sorry, I started from 1:30, right? Yeah, now it's okay. So, any question on that?
Yes, Professor.
Yeah.
The bra of alpha and the kit of beta. This
Yes.
equation, the first part is not very clear for me.
Which
The
one?
first part, which is the imaginary part, the top, the left top of the board.
Here?
Yes, the imaginary part, the first part, half off. It is not that clear for me. I didn't get it.
Okay. So this is this, right? Alpha beta is this. Okay? The definition, right?
Right.
You agree? You
Yes.
agree with it?
Yes.
Now, then what I said, this is the product of two operators, right? A minus A, B minus B. Right? No? You agree with this?
Yes, that's clear.
Okay. Now, I'm saying product of these two things can always be written as half the sum of commutator and plus anti-commutator, because that is clear, or should I repeat it?
That's very clear. Yes.
xy minus yx plus xy plus yx. So what yx cancels, and what remains is xy, half from here and half from here, so it reproduces the origin. So then this is the starting point. So then what we said, I just rewrote explicitly half the sum of the commutator and anti-commutator. Okay?
Yes, I
So
got
just, no?
the commutator xy, which is xy, and the anti-commutator xy.
What we call the, this is xy. This is xy. But x is A minus A and y is B minus B, right?
Yes, I can see it now, Professor. Thank you.
Yeah, and then, okay, so let me repeat again. So this is this thing, and then the observation is that this is the expectation value of commutator and anti-commutator. The expectation value of a commutator of two Hermitian operators is anti-Hermitian And an expectation value of an anti-Hermitian operator is purely imaginary. Right? Because if you have an anti-Hermitian operator, let me call it, I don't know, some name, C. C dagger. Anti-Hermitian means that C dagger is minus C, right? You take the complex conjugate of that, that is psi, C dagger, psi, right? But this is minus psi, C psi, no? This means that this is purely imaginary because it picks a minus sign, right? On the other hand, the anti-commutator is Hermitian, and so if C is Hermitian, it picks no minus sign, so the complex conjugate is equal to itself, so it's real. So this is then imaginary. It means it is I times some real number, capital I, and this is real. This is R, real. So then the structure is this, right? Real plus imaginary part. And then we take the modulus square of this. This is R squared plus I squared, because the modulus square of the complex number is what it is. But this, since both are real numbers, this is greater or equal than one of the two. And what is convenient is to take this, because this gives a non-trivial information, right? So this I is this thing here. 1/4, because we started from 1/2, but we take the modulus square, it becomes 1/4. And this is the modulus, so the complex, this is a number, is the modulus, is the expectation value of some operator, commutator. And this is the modulus square of that number. And so since we started from this is greater or equal than this thing here, right? So then this is greater or equal than that. AB, because, as I said, this is A minus a number, B minus a number. So the commutator, what remains is only the commutator A with B, right? Because the rest commutes. So this is Heisenberg's relation by taking the square root, of course. So delta A, delta B. Modulus, not square, but modulus. Okay. So the best you can achieve is to saturate the bound, right? Again, the best you can achieve is to have equality, but this can be even larger than. So for states which are close to classical states, the best you can do is to have equality here, saturate. We will see how to construct states for which this is saturated. If this is greater than, then it means that you are very quantum, right? Very far from the classical situation, right? Okay. So this is a very general thing, you know, it comes from very basic property of our Hilbert space, vector space, the Cauchy-Schwarz inequality, which is very general. For any space which has a positive definite scalar product, this is true. So this is Heisenberg. Which probably was established first for X and P, right? As we will see soon, review soon, X and P is IH bar, right? So delta X, delta P, yes, obey this relation. Right? We will see soon this thing here. Okay. Other questions? Let's see if I wanted to say anything else. Yes, this is also in the notes, all these things. Okay, so let me move on a little bit more. These are all things that you must have already studied, right? So let's now make contact with some more, maybe or less abstract things. Well, okay, as I was saying, there are interesting physical applications of quantum mechanics defined on finite dimensional vector spaces. This has to do with, for example, if you want to study the, as we will do, the spin, the interaction of a particle with spin, charged particle with spin like the electron, for example, in external electromagnetic field. Sometimes, if you can neglect the orbit, the motion of the particle in space, you can just focus on the internal degrees of freedom of the particle, of the electron, then this effectively becomes a two-dimensional problem, two-dimensional in the sense that the vector space of states is two-dimensional, just two-component vectors, right? So there is some interesting something interesting to discuss even in that case, but in all, apart from this example, all the physical interesting situations arise when particles move in space, right? Two-dimensional, one-dimensional, two-dimensional, three-dimensional space, right? They are subject to some forces, some potentials, interactions, and so on. In that case, one is interested in representing the states in the so-called X basis, where X is the position operator, right? So X, the position operator, you think of it as an operator, okay? And you choose a basis for which X is diagonal, say, something like that, right? Where X is the eigenvalue of this operator. Right? And then what one usually does is to represent state on this basis, right? So if you have some state psi, abstract state psi, By the way, this has some completeness relation, right? Identity. So in this basis, you just do the usual trick. You introduce the identity. This is dx, x, x, psi, right? So this is the component of the vector psi, the abstract vector psi, on the direction x, on this basis x, right? And this is what we call usually the wave function, right? X psi is what one calls the wave function. Function of x, complex function of space, the space coordinate. Clearly, this is one-dimensional case, but you can just put here an arrow here, right? And then you are in three-dimensional space. Okay, say 3x here, right? I mean, nothing changes, right? So here you have, say, if you are in three-dimensional space, this is what is a function of the three-dimensional coordinates, right? So this is the wave function, okay? And now, if the state psi is normalized, right? Then this means that this function must be square integrable, right? Right, because psi, what is psi? It's just dx prime. Let me not put the arrows, so suppose you are in one dimension, okay? This is, say, x prime, the bra, right? Psi x prime, right? And then you have x psi, right? This is what you have, dx prime, no? Double integral, right? But now this is delta, no? Delta x minus x prime. So this becomes x equal to x prime. This becomes the modulus square of the wave function, right? This becomes dx psi of x modulus square, right? All right? So, in order for the wave function to define a state in our sense, meaning that the state must be normalizable, must have length, finite length, and then we divide by the norm in such a way that it becomes 1, okay? This must be the case. So wave function, an honest wave function must be square integrable. Of course, here we go from minus infinity to plus infinity, all the full real line, right? So to make sense, then psi must decay at infinity in such a way that this integral is well defined. That is minus infinity plus infinity psi of x dx is fine. This means square integral, right? And this has the meaning of a probability density, right? Because you can compute the probability of a particle to be in some region of the real line, say this region here, D, you integrate this over the region, and this gives the probability of the particle to lie in this domain, right? This is probability of the particle to be here. And of course, the integral over the full real line must be 1, because the probability of finding the particle anywhere in the real line must be 1. Okay, this, in order for the probabilistic interpretation to make sense, we should require this. Okay. And this generalizes to 3 dimensions. You are just to extend the 1-dimensional case to 3-dimensional case. There is no difficulty in that. Okay. Also, you can express everything in the X basis, and also if you have some matrix elements, say phi, A, psi, you can express everything in the X basis. What you do is just you insert, right? First of all, yeah, there are the matrix element of A in the X basis. So if you insert both here and here the identity, you have dx, dx prime, here you have phi, x, x, right? Identity here, A, x prime, psi, right? This is what you have. So this is dx, dx prime, phi star of x, psi of x prime, right? A x prime, like that, right? Matrix elements in there, and so on. All these things can be. Okay, so this is the X basis, which is what one uses most commonly. Now, I just take one more step and then we stop. Okay, since these are all. So the step is, now we have to give a rule to, if I give you some Hamiltonian, right? T square over 2m plus v of x, this is the simplest type of Hamiltonian. There is a kinetic energy there, right? Plus a potential. Okay. What would be the quantum? What is the rule? I mean, what is the, how we replace this thing with some operator acting on some Hilbert space of function of x, for example, right? This is what we have to answer, okay? So suppose you are in the basis of x, where x is diagonal, so what would be the p? What is p as an operator? The momentum. If x is diagonal, what is p? Right? Of course, we know the answer, but let me just remind you. The one way to identify p is to postulate that p is the generator of translations. This is what happens also in classical mechanics, right? So we assume there is an operator T, and this is the exponential of P essentially. And let me put I over H bar, and this is A is a length. So this is an operator which translates the position by an amount A. Okay. Now, why we need this H bar here? Well, we need something which has dimension of a action, right? Because this is a momentum, this is a length, okay? And this has the dimension of an action. So we need to divide, this must be dimensionless, right? The combination here. So there is a need of some unit here of action, which is a universal, right? H bar, the Planck, reduced Planck constant. This is what we postulate. And TA, what should do TA? When applied to an eigenstate X of the position operator, it should shift the position by an amount A. This is our requirement. Moreover, TA is unitary because P is a Hermitian. Okay. So this is an abelian group element, right? There is only one generator here, and this is the parameter A. Okay. So this is what we demand for the translation to be, right? And so we demand that P is the generator position, which means this, right? This is the finite group element. These are the infinitesimal generators, right? This is, you will see in group theory, this is what you do. And so from this we can get the commutator between X and P. And simply so suppose we take A is very small. If A is very small, I can approximate T with right? T is 1 minus I A P over H bar plus order A squared, right? This is what. And now suppose you take X T applied to X and the other order, T X applied to X. This is what? This is, this shift X by A, right? And this measures that amount. So this is X plus A, right? Okay? On the other hand, this X on X is just X, a number. I can take it out, small x, and this is X plus A. You agree? I repeat it again, this is the A, right? Because this shifts, so this is X times X plus A, and this is X plus A times X plus A, right? Here you have TA, X is a number here, right? So it commutes with that. And this is X plus A, right? Okay. So and this is what then? So this is the difference, X T minus T X and X is this minus that, right? This minus this, no? So this cancels, this is A x plus A. If you are at first order in A, this is essentially the same as AX. Right? Because the correction here would be higher order in A, right? We have to expand this also. This would be X plus order A, but there is already an A here, so this would be A squared. Okay? So this is what it is. And now use that T is 1 minus I A P over H bar to this order, right? And compare the order A, you get the commutator of X and P, right? You get that commutator X and P is I H bar. You replace T with this, but the 1 cancels. What remains? The order A. You have to compare, keep the same order A on both sides, right? There is minus I of H bar, you take it on the other side, and you get A cancels, and you get this. Okay? So from the fact that P is the infinitesimal generator of translations, we obtain this commutator. And this we did in 1 dimension, but it generalizes to 3 dimensions. So you have xi pj, I h bar delta ij, and of course xi xj is I is equal to 0. So these are the relevant commutators. Okay. So this is the canonical commutation relations of X and P. Okay, and by inspection, we see that one way to satisfy this relation is to say that Pi is minus I H bar d xi, right? This for sure satisfies this relation, right? We will derive this maybe in a more fancy way. But actually, it is a theorem, very deep theorem in functional analysis, that this is the only representation of these commutation relations. All the others that you can think of are equivalent to this one. Okay, so this is the representation where X is diagonal, X is X, say, the operator X is just a number, right? The coordinate X, and the P is the derivative with respect to that coordinate with this factor here. So then from this we get the Heisenberg relation that I was mentioning before. Okay, so yeah, this is, I think, for them, we stop here. We will soon arrive at. So what we have to discuss is a little bit, okay, we can rederive this relation and then discuss also another possibility, of course, is to use, instead of the coordinate axis diagonal, you can use P, the momentum diagonal, right? You use state such that this is true, right? And okay, this will amount essentially to, as we will see next time, to do Fourier transform. So if in the x coordinate we have a function phi of x, in the using the p, we will have psi tilde of p, which are just the Fourier transforms of psi of x. Okay. Okay, so then this answers also immediately, if you accept this for the moment, this answer immediately what would be the Hamiltonian P square, the classical Hamiltonian, what will become in the quantum case, okay, is a differential operator, clearly, because this is a derivative, so this is minus h bar square over 2m, say 3 dimensions, okay, plus the potential. And now you see that the situation becomes more complicated because diagonalizing this operator, the Hamiltonian, which is one of the most interesting things in physical problems, to find the spectrum of the energy levels, right, amounts to find the eigenstates of these differential operators, right? And that becomes a problem analysis. You have to solve differential equations, impose boundary conditions, and so on, right? And this can be done in a number of cases, and of course it depends on the potential. If you throw in an arbitrary potential, you don't know, in general, how to solve exactly the problem. We will study some examples, like the obvious one, which is the harmonic oscillator, in which the problem can be solved easily. Okay, so this is more or less for today what I wanted to say. So for next time, maybe you could proceed with this homework that are there on the, actually, now it reminds me that I forgot to press the button which records the lecture. Okay. Anyhow, so, yeah, maybe you can go through this, say, 3, 4, and 5. Of the homework. Actually, 3, 4, 5, and 6 are very simple, and there is no big calculation to do, okay? Six is some playing with the Pauli matrices, use the algebra of Pauli matrices, which one has to do, I mean, get practice with that. Okay, so this, we said 3, 4, 5, and 6. Any questions?
I have a question in parallel to today's lecture that in case of finite dimensional vector space, we know that self-adjoint operator and Hermitian operator are the same thing. But in case of infinite dimensional vector space, I guess there is a subtle difference between them. Could you please shed some light into this?
Well, we see, in the infinite dimensional cases, I think you can still, the definition of self-adjoint or Hermitian can go through formally, right? The problem is how you define the the matrix elements, right? For example, when we say that this operator here is self-adjoint, what do we mean? Okay, because these are some functions, right, of x, okay? So first of all, you have to make sure that, say, when you sandwich this between two functions, say phi star of x minus I h bar e dx psi of x, right? This is what we would, this would be the matrix element of this, right, between two states. In which sense this is self-adjoint, is Hermitian? Well, you have to apply the definition, right? If you take the star of this relation, the complex conjugate, this is a number, what you have? You have phi of x. This is I, right? H bar, d, dx, psi star of x, right? Right?
Yes.
But now you see here, this is applied to this psi star. Now, one would like this to be applied on phi. Right? So what is the step in order to do
Integration
that?
by parts.
It's integration by parts. So you have to be able to neglect a total derivative, right? This is the same as minus I h bar d dx phi of x, right? Psi star of x. No? If the total derivative is d dx is phi psi star, right? Say plus infinity minus infinity, right? So this is this actually, right? The boundary term, right? So this has to be zero, right? Otherwise this manipulation would not be true. So in order for an operator in infinite dimension to be self-adjoint, you have to specify the boundary condition on the space of functions on which you act, right? So in this case, for example, it must be essentially square integrable functions, in which case then P is defined as a differential operator is self-adjoint, is Hermitian. So every time you have to make sure that the space of function on which it acts must have the right property. So it's a matter of boundary condition, which in final dimension does not exist simply.
So in case of square integrable function, this condition is automatically satisfied, right?
Yeah. So typically when you have function defined on the full real line or the full space, you have to impose boundary condition at infinity, which makes sure that things like that are well defined.
Thank you.
So it's much more complicated, of course, the situation in infinite dimension. But with this condition, then this is true. I mean, this operator is self-adjoint because of this. Right. And the same is true for this type of operators even more, right? Even here, when you argue for the self-adjointness of H, you have to do partial integrations. Right? Yeah, that is always, you have to be careful about these things. Yeah. Okay. For today, it's okay. If there are no other questions, we close here. Okay. See you next time.
Thank you,
Thank you, Professor.
Thank you, Professor.
Thank you.